All right. So there are three states of matter: gas, liquid, and solid. In Chapter 5, we're going to talk about all three states of matter, but we're only going to really focus on heavily the gas phase, okay? Because in the gas phase, the reason the gas phase is so interesting is because gases have certain characteristics like the volume of a gas, or the temperature of a gas, or the pressure of a gas. It has all these characteristics that you don't find in other states, right? We don't talk about the pressure of a liquid, or, I mean, you can, but not necessarily we don't conceive of it in the same way. In the gas phase, it's really easy to conceive of those pressures, the volumes, those phases, those characteristics, and we can really visualize the molecules and what they're doing. And it makes it very easy to perform mathematical calculations as well. And the other reason the gas phase is so interesting is because it relates directly to moles. So the volume of a gas relates directly to moles. And that is the volume of any gas. So if I have 22.1 liters of a gas at a pressure of 1 atmosphere, and at 0 degrees Celsius, okay, temperature 0 degrees Celsius, pressure 1 atmosphere, and the volume is 22.1 liters, the gas volume, that means I have 1 mole of a gas, independent of its identity. It could be hydrogen gas. It could be oxygen gas. It could be nitrogen gas. It could be carbon dioxide gas. It could be methane gas. Oops, CH4. It could be any of those. And if I have 1 mole of it at 22.1 liters and 1 atmosphere and 0 degrees Celsius, I have, 1 mole of it will have these parameters at these temperatures and pressures. Okay? So that's why gases are so interesting to us, because it doesn't matter what its identity is. They're so spread apart, the gas particles, that they will occupy the same volume at those pressures and temperatures. Okay? And we're going to see how that works. So here we have, you can go through different physical states, changes in those physical states, okay? Simply by increasing or decreasing the temperature, okay? You can go through the gas to the liquid to the solid phases. Everything can. So oxygen in the air, we can condense it to a liquid. It can condense. It doesn't only exist as a gas. It can be condensed to a liquid, and it could even be frozen if you get the temperature cold enough. You could freeze that oxygen, and then it would evaporate after it heated up, right? Some frozen things will go straight from a from a solid phase to a gas phase, like carbon dioxide, dry ice. Have you ever seen dry ice? Have you guys seen dry ice? Have you ever seen it melt? Hopefully not, because it doesn't. It doesn't melt. It evaporates. When you put it on here, you see it like steaming. It looks like it's all hot and steamy, right? Well, for it really is hot and steamy in that room. Okay? So it's evaporating because it doesn't melt. It just goes straight from the solid phase to the gas phase directly. And that has to do with the pressure of the atmosphere. If you change the atmospheric pressure, that would force it to melt. It would force it to melt. And then it would melt and then evaporate. Okay? Just like ice does. Ice will melt, and then at a high enough temperature, it will then evaporate. Okay? So water goes through all 3 phases. Carbon dioxide would go through all 3 phases if it was at different pressures. Okay? So here are some characteristics of these different states of matter. So gas, the volume of a gas, gases fill their container. So if I had a container and it was full of gas and I opened it, the gas would escape. What is the new shape or volume of that gas? This room. It now escapes into the room and fills the room. with all the other gases that are in here. So it will take the shape and the volume of its container. It will fill the entire container. Okay? I can condense gases, so if I take gas particles and I push them together into a smaller volume, I can do that. But you cannot really do that. Compressibility is high for gases, but for liquids, not really, and for solids, it's virtually incompressible. Okay? Makes sense, right? Because gas particles are so far apart, you can push them together. Bring them close together. But then you bring them so close together that the pressure builds up so high that they burst out of whatever container they're in, right? So they can be compressed, obviously, but only to a certain extent, because you're never going to force them so close together that they would then go into the liquid phase, okay? Okay, so densities of gases are low because the particles are so far apart. Densities of liquids are high, and of solids are high as well. Particle motion. Gases have free particle motion. They're free spirits, right? They're all over the place. They're doing whatever they want. Liquids, they have to slide past one each other. So now they're touching. The liquid particles are touching, but they're rolling over one another, okay? So they're they have to slide past each other. In solid phase, the particles they're vibrating. They're in fixed positions. They're stuck in one position, but they're vibrating because they still have energy. This table has particles vibrating. They're vibrating because they still have energy. How would I stop them from doing that? I would have to make the temperature cold enough to get rid of all the energy. That would be absolute zero. You'd have to reach absolute zero so the particles would stop vibrating completely. Okay? Okay. The distance, intermolecular distance, obviously very large between molecules, and that's why that relates directly with density, right? So very low density means the intermolecular distance is very large. Okay, for liquids, their particles are close together. They're even touching, and obviously even closer in solids, with an exception: water. Water in its solid phase is less dense than in its liquid phase, right? You guys prove that every time you put some ice in your water. What does it do? Does it sink? Does the ice sink in your water? Nope, it floats, which means the ice is less dense than the liquid phase, which is uncharacteristic. Most things don't do that. Most things, when they go to the solid phase, the particles get even closer, more dense, and they would sink in their liquid phase. But ice doesn't do that. It floats. It's less dense. And that has to do with the strong attraction between water molecules. So those strong attraction between water molecules that creates things like surface tension and such, when it freezes, it causes those particles to expand out a little bit. And now they're less dense than in their solid phase. Okay? Okay, so we're going to talk first about the gas phase. And this is the most interesting phase, and it's the one we're going to focus on the most. So chapter 5, for the most part, is about gases, with a few little blurbs about solids and liquids. Okay? So the gas phase, when we talk about gases, we consider the gases to be in an ideal way. Okay? So an ideal gas is a model of the way that gas particles behave at the atomic or molecular level. So it's the ideal way that they behave. Okay? So we're modeling them and how they should behave, or how we would predict them to behave at the molecular level. So with that, we can measure the following of a gas: the temperature, volume, pressure, or the mass. Okay? So if we change one of these, it will cause the change in something else. If I change the temperature, that might affect the volume. It might affect the pressure. Okay? So that's what we're seeing. We're seeing if we change something, if we change how much the mass of a gas, meaning I have more gas particles than I had before, that might affect the volume or the pressure, okay? So that's what these scientists a long time ago were doing. They were taking gases at certain volumes. They were changing certain parameters like the pressures or the temperatures or the volumes to see how it affected the other things associated with it, okay? So in these gas laws, we are going to label moles of a gas as N, volume of a gas as V, temperature as T, and pressure as P. So when you see N, V, T, P, you know what those stand for. N stands for the moles of a gas, V for the volume, T for the temperature, and P for the pressure. Pressure is what we consider to be the force of the gas particles per an area unit, okay? So how much force is being exerted on this one little area here? That's what we consider to be pressure. And we'll see how we measure pressure here in a little bit, okay? This is called a barometer. Barometers measure pressure, okay? So here I have a liquid. It's a liquid metal, liquid mercury. Mercury is a liquid at room temperature. If I stick a capillary tube into the mercury will shoot up that capillary tube based on the pressure being exerted on it from the outside. So if I lower the pressure out here, then this would lower. If I increase the pressure out here, it will cause it to shoot up even higher. Okay? So this is a very simple instrument for measuring pressure, but it is very accurate. So this is how we obtain our pressures measurements. Okay? Here, at 1 atmosphere of pressure, the mercury is moving up this capillary tube 76 centimeters, which is 760 millimeters. And we say that that pressure measurement is 760 millimeters of mercury, mmHg. Hg for mercury, millimeters mm, millimeters mercury. Okay? Which is equivalent to 760 torr, which is 76.0 centimeters mercury. Okay? And 760 millimeters mercury is equal to 1 atmosphere of pressure. This unit, atmosphere of pressure, is the one that we will become the most familiar with. But you will see 760 millimeters mercury and so forth. Okay? So you will have to also become familiar with that one. Okay, so how do gases behave? So gases are made up of small atoms, right? They're individual particles. And they're bouncing off the walls. They have all this energy. That's why they're in the gas phase, because they have enough energy to break away from other oxygen molecules or other carbon dioxide molecules or other nitrogen molecules. So they have enough energy to not be attracted. So to force attraction, you have to decrease temperature. If you decrease the temperature, attractions will increase between like particles. Okay? But if you increase energy, that breaks attractions. Just like if I was going to break a chemical bond, an actual chemical bond, I would have to heat up a substance. And that would allow for the bond to break. If I absorb enough energy, absorbing energy will break bonds. Okay? It's the same with attractions between like molecules. If I heat it up, those attractions will become lower and they will separate. If I cool it down, they will find one another and they will be attracted to one another and they will condense. Okay? So gas particles are individual atoms and they're in constant random motion. Okay? They're just bouncing off the walls, going everywhere. It reminds me of my kids. Just random motion, perfect. They're little gas particles. That's what they are. Okay? The distance of separation is very large compared to size of individual atoms or molecules, right? So if you consider how big an atom is, and then you consider how far they are apart when they're in the gas phase, it's almost incomprehensible to a single little atom how far apart his neighbor is. They don't even know they're there. They don't even know they exist. They're so far apart. Okay? Essentially, if I'm a gas particle, there's another one down at Walmart here in Calabria somewhere. I don't even know it's there. Okay? So that's how far apart these gas particles are. They're so separated that they're just acting all on their own as individual particles. Okay? So gas is composed of mostly empty space. That's what gas is mostly. Okay? Gas particles behave independently. So if you want to be independent, you have to be a gas particle. Okay. Collision of gas particles. They collide with one another, and they collide on the walls of their container, which exerts the pressure on the container. Okay? The faster they're moving, and the more particles that are colliding, the greater the pressure. So if only 3 or 4 particles are colliding per second, if I increase that to 10, now there's more particles colliding with the container. The pressure of that container is increasing. How do I do that? I increase the temperature. It causes them to move faster. More particles are colliding with the wall of the container per second. Okay? And that's creating a pressure within that container. So as they collide, either with the walls of the container or with one another, energy is transferred from one atom to the other one. So they're not losing energy; they're just transferring that energy. Boom, 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 boom. They just keep going. Okay. And those cause random changes in direction of the molecules. So I'm flying this way, and then I hit somebody. We hit, and then that forces me to just veer off that way. Okay. It's like billiard balls, right? Coming and veering. So that's what they're doing. They're just going around, bouncing off everywhere. The energy of these atoms increases or decreases with temperature. So you increase the temperature, you increase the kinetic energy in the system. You decrease the energy, you decrease the kinetic energy available to perform work. Okay? So they're speeding up or they're slowing down. That's what the particles are doing as the changes in temperature. Gases are compressible. Because they're so far apart, the particles are so far apart, we can force them to come closer and closer together. But as we do that, we're causing more and more collisions on the walls of our container, which is increasing the pressure. And eventually the pressure is going to be really high, and we have to have a really strong container for really high pressures. Okay, or else it's just going to burst open. Okay, they expand to fill their volume. They diffuse throughout each other. So because there's so much empty space, a gas particle and another gas particle, if you release a gas from here into this room, it will fill this container. It will diffuse throughout the container because there's nothing in its way. It's just everything all over the place, randomly, everything's going everywhere. Okay? And it will eventually fill the container, and they'll be spread apart. It will be homogeneous. Those gas particles will become homogeneous with all the other gas particles in this room. They have low densities. They exert pressures. They are most ideal at low pressures and high temperatures. Why? Because at low, which is a hard thing to obtain, you could imagine, low pressures, high temperatures, right? So usually high temperatures would indicate high pressures. So if you want to create the most ideal situation you can, you want to have the least amount of collisions or interactions. That would mean low pressures, but high temperatures, because at lower temperatures, the particles are actually starting to interact more with one another. So to break those interactions, you need at high temperatures, low pressures. Okay? And that's an ideal gas. Gases, here's a look at how gases diffuse. So here is hydrogen chloride. Look at its molecular mass, 36.5 grams per mole. Here is ammonia. Its mass is 17 grams per mole. This one is significantly lighter than this one. Okay? So if I start if I release this gas and this gas at exactly the same time, because that one is lighter, the ammonia, look at its diffusion, its speed of diffusion. It's much faster. It has a much faster speed of diffusion than the heavier one. And that's how gases diffuse, based on how heavy they are. So the lighter you are, the faster you diffuse. So hydrogen, the lightest gas, H2, would diffuse faster than any other gas. Okay? So if that's important to you, then hydrogen diffuses faster. Okay? All right, now let's get into the math part of this. Okay? Which you've all been waiting for. I know you love it. So Boyle's law. Boyle's law is going to talk to us, or was derived by the scientist Boyle, okay? And he came up with the ideas of how is pressure going to affect the volume of a gas? That's what he wanted to know. So he did some experiments taking a cylinder that can, freely move, or I think this is going to be how we show all of this, but basically you have an expandable volume. It can contract or get bigger according to the pressure of the system. So here I have these gas particles. They're bouncing around. They're creating a pressure in here. Okay? So you can't see that very well, can you? Here, this first one, it's 1 atmosphere and 10 liters. Okay? So 1 atmosphere, 10 liters. If I increase the pressure to 2 atmospheres, what happens to the volume? It goes down by exactly half. So you double the pressure, what happens to the volume? It goes down by 1/2. Okay, well, what if I double the pressure again? Then the volume gets cut in half once more, right? So that's what we see is happening. So it is proportional, right? You double it, you cut it in half. You double it, it's inverse. There's an inverse relationship here, okay? Consider a balloon. I have a balloon. If I increase the pressure, what is going to happen to the volume of the balloon? And this is a trick question, so think carefully. Is it going to get bigger or smaller if I increase the pressure being exerted on the balloon? What do you want to say? You want to say, if I increase the pressure, what happens to the balloon? But that's not what happens. If I increase the pressure, what's going to happen to the volume of the balloon? Because we're not talking about the initial pressure in the balloon. We're talking about the final pressure in the balloon. And how do I change the pressure of the balloon? I don't do it inside of the balloon. I do it outside of the balloon. Right now, we have a pressure that's being exerted on us. It's a pretty heavy pressure. 1 atmosphere pressure. It's a column of air that's weighing down on me right now, all the way up to the atmosphere. All of those particles of mass are sitting on my shoulders from here all the way up to space. That's a heavy pressure of gas on my shoulders, okay, being exerted on all of us. So that balloon has a pressure being exerted on it. And the pressure of that balloon can only change if I change the pressure outside, not inside. Because if I change the pressure inside, what will happen? It will expand. But once it does, it only expands. When does it stop? It doesn't necessarily have to pop. When would it stop expanding? It could pop, but when would it stop?
When the latex stops.
When the pressure inside and outside of the balloon are the same. That's what determines the pressure inside the balloon. What pressure is outside? right? So if I have my balloon, out here is 1 atmosphere. Let's say it's 0.5 atmospheres in here. This balloon will expand until the pressure inside is 1 atmosphere as well. Now I have 1 atmosphere outside and 1 atmosphere inside. It cannot expand anymore. But if I decrease the pressure outside, let's say I change this to 2 atmospheres, what's going to happen to the balloon? Think about me pushing on it. You increase the pressure outside, I'm pushing on it. Now it's going to decrease the volume of the balloon, right? So if I decrease this pressure outside, what would happen to it? It's going to expand until the pressure inside and outside are the same. That's what stops it. That's what's going to stop it. So if I have a balloon here down at sea level and I start walking up a mountain, what's going to happen to that balloon? Well, as the pressure gets less and less as I move up and up the mountain, it would go like this. It would expand. That balloon would expand because the pressure is lower up in the mountains than it is down here. There's more pressure here, more column of air on me right down here than if I walk up. Less column of air on me up in the mountains. Less pressure. So it would expand bigger as you walked up. So you have a flat balloon down here, walk up into the mountains. Take care of that. Okay? I know. It only just have to do that. Not a big deal. Okay? All right. So this is the relationship between pressure and volume. They have an inverse relationship. If the pressure increases, the volume will decrease. If the pressure decreases, the volume will increase. Okay? Because we are talking about the outside pressure, not the inside pressure. Because the pressure inside will expand until it matches the outside pressure. So it's the outside pressure that counts. Okay, now this is the mathematical law. I like to actually write it as P1V1 equals P2V2. But P initial, volume initial equals P pressure final, volume final. That's fine as well. PIVI equals PFVF. That's okay. P1V1 equals P2V2. Same thing. Okay? So here we have a question. If I double the pressure to 2 atmospheres, okay, a gas occupies 10 liters at 1 atmosphere. If I double the pressure to 2 atmospheres, it would cause the volume to become, okay? And so it wants to know. So you have 10 liters, 1 atmosphere, and you double the pressure. So it's going to cut it in half, right? So if you increase the pressure, the volume will decrease by that same factor. So it goes from 10 to 5. And here they're showing it mathematically. 10 liters times 1 atmosphere, that's what I started with. I changed the atmospheres to 2 atmospheres pressure. So 10 times 1 divided by 2, 5. So it ends up being 5 liters. It would decrease to 5 liters. Okay, let's practice a couple. A 5-liter sample of gas at 25 degrees Celsius and 30 atmospheres is compressed at constant temperature. Look at this. That's a distractor. It has nothing to do with this question. Temperature is not part of this question. How do I know? Constant temperature. The temperature didn't change, therefore it doesn't affect the volume or the pressure. Okay? So because it's constant, it is not part of this question. So don't try to put it in there somehow. Okay? Just leave it off. So P1 V1 equals P2 V2. What are we solving for? What is the new pressure? So I want to find V2. V2 is equal to P1 V1, P1 V1, divided by V2. So I'm sorry, P2. So I move P2 down here. I get it away from V2 by dividing it to the other side. Okay? That's the equation I want to use. So I just simply extract my information. What's my initial pressure? Three atmospheres. 3.0 atmospheres. Okay? What's my initial volume?
5.
Okay? 5 liters. What is my new pressure? I'm sorry. What am I saying? What is the new pressure? Why did I do V2 here? Gosh, you guys. Just. Okay. Okay, what is the new volume? No, new pressure. What is the new pressure? So divided by 1.0 liters. Okay? That's my final volume. So 3 times 5 divided by 1, 15 atmospheres. That's tremendous. Okay, that's a tremendous pressure. So that's how we would solve that question. Okay, now, first off, how do I know I need to use Boyle's law for this question? Because you're not going to have sections like Boyle's law section, Charles' law section. Okay? It's going to be a bunch of questions all together, and you're going to have to identify, oh, I need to use Boyle's law here. Oh, I need to use Charles' law here. Oh, I need to use the ideal gas law here. How are you going to identify that? How would I do it for this question? Okay? Well, what is changing? The volume and the pressure. That's how I know it's Boyle's law. If you have volume and pressure changes, then you use Boyle's law. Temperature is not changing, so I know I don't need it. If volume, pressure, and temperature were all three changing, then I would use a different law, and we'll look at that law in a minute. But because I'm not doing volume, pressure, temperature changes, I use Boyle's law. Boyle's law deals with changes in pressure and volume. Okay? Do you have a question?
Do you have to say increases or decreases? Or
You don't have to. Well, if the question is, what is the new pressure, then you just have to say the new pressure is 15 atmospheres. Okay? And usually you just choose whichever answer is 15 atmospheres. Right? Okay, a 3.5 liter sample of a gas at 1.0 atmospheres is expanded at constant temperature once again until the pressure is 0.10 atmospheres. What is the volume of the gas? So what am I solving for now? Volume. V2 equals P1 V1 over P2. Okay? So I just took the Boyle's law again, P1 V1 equals P2 V2, and I solved for V2. Okay? What is the volume of the gas? This time I'm actually doing it for that one, not like last time. Okay? So here I'm going to identify everything that I need. What is the initial pressure? 1 atmosphere, right? What is the initial volume? And what is the final pressure? .10 atmospheres, right? Atmospheres cancels. I'm left with liters. That's what I want. I want volume. Over here, the liters canceled. I was left with atmospheres. That's what I wanted. I wanted pressure. Okay? So that's always a good check to make sure you're doing it right. Yes?
How do you know what numbers goes when for the P1 and P2?
So P1 is the pressure. Pressure is always units of atmospheres. So 1.0 atmospheres is my initial. This is P1. That's what it started at. And it went to P2, 0.1 atmospheres. That's what they're telling me. A 3.5 liter sample of gas at 1 atmosphere is expanded, so it changed to 0.1 atmospheres and a new volume, what is the new volume? Okay, so that's how I know where everything goes. So I like to solve for it here first, and then I can fill in, because then it's easy to know what to fill in. So 1 times 3.5 divided by 0.1. What's that? 35 liters. So this expanded from 3.5 liters to 35 liters. Okay? Is that what we expected it to do? Should it have, so the pressure did what? Pressure decreased, so volume should increase according to Boyle's law. Right? Okay, let's look at Charles' law now. It's getting warm in here. You guys feel like it's getting warm in here? Or is it just me? Okay, Charles' law. Volume of a gas varies directly with the absolute temperature. So Charles looked at changes in volume based on changes in temperature. Okay, so he wanted to understand, if I change the temperature, what happens to the volume of a gas? Okay, so he came up with his law as well. Volume over temperature is equal to a constant. So let's see how that works here. If I have this volume and pressure of a gas, so 1 atmosphere, 1 liter, okay, and the temperature is 273 Kelvin. So the pressure is going to be constant. You can see the pressure isn't changing with any of these. So the pressure is held constant, but the temperature of the system is changing. So I'm going to go from 273 to 546 to 1092. So I'm doubling the temperature each time. Every time you double the temperature, what do you think happens to the volume? The volume also doubles. So from 1 liter to 2 liters as I double the temperature. And then from 2 liters to 4 liters as I double it again. So is this an inverse relationship? Is this the same as Boyle's law, where if one goes up, the other one goes down? No, this is a direct relationship. If one goes up, the other one goes up. If the temperature increases, the volume will increase. Okay? That one's a little better than Boyle's law to comprehend. We can see that happening, right? You increase the pressure of something, the volume would increase. So if you heat up the gas particles inside of the balloon, the volume is going to increase. The pressure isn't going to change. It's going to stay the same, but the particles will cause the volume to increase. Okay? So that the pressure inside and outside will equilibrate and be the same. All right? And that's what's happening here with this cylinder. As I increase the temperature from 273 to 546, the volume is increasing. Okay? So Charles' law is simply V1 over T1 is equal to V2 over T2. This is how I mathematically write a direct relationship. If it's an indirect relationship, then it's multiplied. V1 P1 equals V2 P2. Okay? That's indirect. Direct is by division. Okay? So here, a gas occupies 10 liters at 273 Kelvin. If I double the temperature to 546 Kelvin, it would cause the volume to become twice as much, right? So I go from 10 liters to 20 liters. And they're showing mathematically how that would be. Okay? So it would increase to 20 liters. So let's practice. A 2.5 liter sample of gas at 25 degrees Celsius is heated to 50 degrees Celsius at constant pressure. Will the volume double? So, what do you think? Will it double?
Yes.
Did I double the temperature? This is a trick question. Did I double it, the temperature?
Yeah.
what did you notice about temperature here? (273 Kelvin, 546 Kelvin. Okay? So whenever we work with temperature in the gas laws, it must be in Kelvin temperatures. Degrees Celsius temperatures are unacceptable. And we're going to see why right here. How do I change from Celsius to Kelvin? Add 273. So 25 plus 273. What is that? Okay, so we get to 298. 50 plus 273. What is it? Say it again. Did I double the temperature? What would have been double the temperature in Kelvin? What would have been? 298 times 2, what is it?
596.
Good. So 596 Kelvin, 596 Kelvin would have doubled the temperature. Did you double the temperature by going from 25 to 50 degrees Celsius? No, you did not. Okay? So this is simply trying to help you understand that you cannot use degrees Celsius to calculate gas law questions. It must be in Kelvin temperatures. You have to have it in Kelvin temperatures to show the relationship. Okay? So we would use these temperatures. Okay? So would it double? No. What would be the volume? How could I figure that out? V1 over T1 equals V2 over T2. What am I solving for? V2. Good. Okay, now, some of you might look at this and say, cross multiply, I can do that, Mr. Crandall, no problem. Fine. Okay, but some of you may look at this and say, I don't know what to do with that. How am I going to rearrange? How am I going to solve for V2? This is my recommendation. Get everything off the bottom. Get it off the bottom. Get a new equation. V1 T2 equals V2 T1. Get it off the bottom, and now I can easily visualize exactly what I need to do to solve for V2. Look what V2 equals. V2 equals V1 T2, and now divide by T1. Okay? So putting it in that format, getting everything off the bottom, putting it in that format just allows me to visualize what it should be. Okay? So that I don't make a mistake. Because otherwise, I'm here and I'm trying to do whatever and I might make a mistake. Especially if I'm solving for T2. Okay? That's where you guys really struggle. If I was solving for the new temperature, it's not so easy. It's not easy to see what I'm doing. So, move it up here. Now I can easily see T2 equals V2 T1 divided by V1. Okay? And it makes it very easy to know I'm getting the right equation. Okay, so how do I solve for it then? So V2 equals V1 T2 divided by T1. Okay? So what is V1? What is my initial volume? 2.5 liters. Now, this is another place where people make mistakes. What temperature am I going to put on top? 323 Kelvin. Okay? Not 298 Kelvin. Do you see how some people can make that mistake? Don't put the 298 because look at your equation. What am I putting on top? Not T1, I'm putting T2 on top. Where am I putting T1? 298 Kelvin on the bottom. Kelvins cancel. I'm left with liters. This will be my answer in liters. 2.5 times 323 divided by 298. What do you get?
2.7.
What is it again? 2.71 liters. Okay? That is my new volume. So it definitely did not double. It only went from 2.5 to 2.71. That's nowhere close to doubling, right? I'd have to go to 5 to double. And to double, I would have had to go to a temperature of 596 Kelvin. What temperature would be required to double? 596 Kelvin. We already answered that, right? Okay? So this is 2.71 liters. Okay, so that's Charles' law. Okay, if you combine Boyle's and Charles' law together, you get something called the combined gas law. So P1 V1 equals P2 V2, right? And V1 over T1 equals V2 over T2. So these are my gas laws. If I combine them, I would say P1 V1 and then V1 over T1 equals P2 V2 and then V2 over T2. Okay? So this right here is the combined gas law. That's the combined gas law. P1 V1 over T1 equals P2 V2 over T2. You should know how to get that law from Boyle's and Charles' law. It might not be a reference material, so you need to make sure you know how to get it. So if it's a combined gas law question, then I need to know what that law is that I'm going to use. Okay? P1 V1 over T1 equals P2 V2 over T2. So here we're going to show how we would use that and how I would identify that it's even a combined gas law question. Calculate the volume of N2 resulting when 0.1 liters of a gas is heated from 300 Kelvin to 350 Kelvin at 1 atmosphere. Okay, well this isn't a very good combined gas law question because look at the initial and final pressures. They're the same, right? So, whatever. So the idea here, I guess, is that you don't have to really, you can use the combined gas law to solve for a volume temperature change because that's Charles' law, or you can just use Charles' law, okay? But if you do use the combined gas law, because you see pressure, volume, and temperature in the question, the pressures are the same, so they would just be the same on both sides. They would end up canceling. They would just cancel. They wouldn't actually end up being part of the calculation because they would cancel. Okay? So you don't necessarily have to include them. But you would need to do the volume and temperature changes here to find the final volume. So what is the equation we would want to use? Well, move everything to the top. Remember, get it off the bottom, move it to the top. So we have T2 P1 V1 equals P2 V2 T1. I moved it from the bottom to the top. Now, I want to solve for, calculate the volume of N2, so V2. I want the new volume. What is the new volume after these changes? So it equals T2 P1 V1, V2 equals this, right? Divided by everything around it. Divided by P2 T1. Okay, that's going to equal V2. So do you see how if I move it to the top, I can easily see what the equation should be. And then I can easily rearrange it. Okay, so my final temperature, once again, final temperature is on the top, not the bottom, is 350 Kelvin, times my initial pressure, which is 1 atmosphere, times my initial volume, which is 0.100 liters, divided by my new pressure, which is 1.00 atmospheres. See how they cancel? So because they stayed the same, they just end up canceling. Divided by my temperature, my initial temperature, which was 300 Kelvin. So Kelvin temperatures cancel, atmospheres cancel, I'm left with liters. So 350 times 0.1 divided by 300. Okay, so what do I get there? Okay, 0.12 liters. Okay, that's my new volume. Okay, so which we expect because the temperature increased, so there should be a volume increase. Oh. Okay, so here they're going to show it. Okay, so another practice with the combined gas law. Calculate the temperature when a 0.5 liter sample of gas at 1 atmosphere and 25 degrees Celsius is compressed to 0.5 liters of gas at 5 atmospheres. So we have atmosphere pressure changes, we have liter changes, and we want to calculate the temperature, the new temperature. So P1 V1 over T1 is equal to P2 V2 over T2. Okay, solve for what? What are we solving for? T2. Do it. Solve for T2, plug in your information, and tell me the new temperature of this system. What did it change to cause those changes? Move it all to the top. Move T2 and T1 up. Okay. Good. Excellent. Now isolate T2. T2 equals this. And then divide it. This will be divided by these things. Makes sense? Okay, is anybody finding an answer? What do you get? Okay, so the new temperature is 2,980 Kelvin. Okay, so we started at 298 Kelvin. And to cause these changes, it increased to 209,800. Is that consensus? Is anybody else getting that? No? What are you getting? 149 Kelvin? Okay, so let's find out which one's right. So, should the temperature increase or decrease? Look at what happens to my volume. 1 atmosphere to 5 atmospheres. If the pressure increases, that's atmospheres, that's pressure. Okay, so what happened to my volume? 0.5 liters to 0.05. So volume went down, so pressure should have gone up, which it did. And if pressure goes up, temperature should also increase. If volume goes down, temperature should go down. So we need to calculate this. We can't just look at that. Okay? So P1, 1.0 atmospheres times V1, 5.0 atmospheres. Okay? Divided by, times, that's what I want to get. I want to find T2, right? Sorry.
So shouldn't it be P2, V2, T1 divided
I'm not starting out very good. I was using this equation. I should. So T2 equals, okay, so that's where we're starting. T2 equals P2, V2, T1 divided by T1, P1, V1. There we go. Okay, so that's what I should be doing. Okay, so P2 then is what I want to start with, and that's 5 atmospheres. V2, which is my 0.05 liters, times my initial temperature, which was 298 Kelvin. Okay, and I'm going to go to P1, which is 1 atmosphere, times my volume, V1, which was 0.5 liters. Okay? So, is this how you guys were doing it? What are you getting?
I got 149.
This is 149?
Mm-hmm.
Okay. So the temperature did decrease. Good. Okay, so that's combined gas law. The last law, oh, there's more to come, guys. This isn't the last one either. So the next law is Avogadro's law. And Avogadro's law deals with changes in volume versus changes in the number of moles. So if I increase the number, think about the balloon example again. If I blow into it, I'm blowing carbon dioxide into the balloon. I fill it up to a certain amount. Okay. If I blow into it more, I'm adding more moles of gas, right? And it's expanding to an even greater volume. So it's a direct relationship. The more moles you have, the greater the volume. So that's why this law is through division. V1 over N1 equals V2 over N2. It's a direct relationship. Okay? for Avogadro's law. If 5.5 moles of carbon monoxide occupy 20.6 liters, how many liters will 16.5 moles of carbon monoxide occupy at the same temperature and pressure? Okay, so temperature and pressure are held constant, so we don't care. So moles and volume are changing. That's what we care about. How many liters? It wants to know the new volume. So we're solving for the final volume here. V1 over N1 equals V2 over N2. Let me get everything off the bottom, put it on top. V1 N2 equals V2 N1. Okay, so I want to solve for the V2. V2 equals V1 N2 over N1. That's the equation that I would use. Okay, I'm going to say that V2 therefore equals 20.6 liters times N2, which is the second number of moles, which is 16.5 moles, divided by the initial number of moles, which is 5.50 moles. Okay, so 20.6 times 16.5 divided by 5.5. What is it? 61.8. Okay, so we get 61.8 liters through that calculation. Okay, molar volumes of a gas. So like I said earlier, it doesn't matter what identity you have. The volume of a gas will be the same if you have 1 mole of it, no matter what it is. It can be hydrogen, it can be oxygen, it can be nitrogen. Okay, they will occupy, all of them will occupy the same volume of space, which is, which is 22.4 liters. Okay, it will be 22.4 liters for any gas that has a temperature of 0 degrees Celsius, 1 atmosphere, and you have 1 mole of it. So we're going to actually see why that is through another law called the ideal gas law. Okay. So here, densities for gases are easily calculated. Density is mass over volume, right? Usually grams, but in case of densities, we're going to say per liter. And the reason is because we're going to use this 22.4 liters as the volume of our gas. And we just simply need to use the mass of it, 4.0 grams, divided by your 22.4 liters. So if it's helium gas, has a mass of 4 for every 1 mole of it, right? Nitrogen gas would have a mass of 28 for every 1 mole of it. So 28 divided by 22.4 would give me the density of that gas. So if you know the mass of the gas for every 1 mole of it, you simply divide it by 22.4. You would know the density at 0 degrees Celsius and 1 atmosphere of that gas. Okay, so that's how densities of gases are obtained. We're not going to do a whole lot with densities, but that's how it would be. Next time we will talk about the ideal gas law.